So, we are going to continue our discussion on heat sinks. Before we move forward, we will just summarize quickly what we discussed on heat sinks. We looked at the first order type modeling of heat sinks, and then we discussed some existing models that may or may not work for all kinds of heat sinks, and then we use heat exchanger theory to come up with a very simple model that with experiments also has shown good results. And then we looked into natural convection cooling of parallel plates, which could be used either for natural convection heat sinks or for parallel boards, PCBs that are cooled by natural convection. So, there was some discussion on the natural convection in terms of two limits, which was d tending to the spacing, d being the spacing between the boards or the fins tending to 0, which ended up being a fully developed flow right from the beginning, and we developed a heat transfer rate for such a scenario, and the other limit being d tending to infinity, which means that the spacing between the boards are so far apart that gave an isolated plate, that is, there is no interaction between the plates that are in the system. So, with the two limits showing that the heat transfer rate, one goes proportionally increases as a function of d and the other one decreases as a function of d. So, once we tried to put them together, we found that there was an optimum or maximum heat transfer rate, and that we discussed as the optimum spacing between the boards or the fins. So, just to summarize, we will go back and look at this. This is the limit where we saw that the d tending to 0 limit, this is the d tending to 0 limit where the flow was assumed to be fully developed all the way from the beginning at the entrance to the entire length of the plate. So, this limit was derived using m dot Cp equal to, that is, the heat transfer rate was obtained using m dot Cp into delta T. Delta T is nothing but the maximum or outlet temperature minus T inlet. The T out is nothing but the maximum temperature, that is the plate temperature, that is the maximum temperature the outlet fluid can reach is only the maximum temperature of the plate, that is the plate temperature. So, you use delta T equal to T plate or T wall minus T in and m dot Cp. However, how do we calculate m dot? It was not clearly discussed in the last session. So, but however we will discuss it here. M dot is equal to rho into the spacing is d, dw, w being the width, and dw times the velocity. In this case, the velocity we will assume has units, the velocity is u. So, that is that. So, how do I figure out what is my velocity? So, this velocity is nothing but, because it is a natural convection heat sink, it is a balance between the buoyancy force g beta delta T. This comes from beta is the expansion coefficient, g is the acceleration due to gravity, delta T is the same delta T we discussed here, being balanced by the pressure gradient. How do I obtain pressure gradient? It just comes from the friction factor relationship, and it is nothing but Fr or F divided by the hydraulic diameter half rho u square. So, with this now I can calculate u by substituting over here and writing it, taking that velocity, plugging it in the mass flow rate, taking the mass flow rate, plugging into the q equal to m dot Cp delta T expression. And then, because there are n number of plates, 1, 2, 3, here it is a 4 plates are shown here, that can be obtained assuming L by D, because we are ignoring the thickness of the plate. So, that is the expression for d tending to 0 or the fully developed flow limit. Now, on the other extreme, which is the isolated plate limit, the boundary layer is not interacting with the other side boundary layer. So, there is the core of the flow is not at all interactive. So, this is at the same as inlet temperature, and this is true all the way to the end is what is assumed. So, the assumption is that we will treat that as if the boundary layer grows on both sides, and it is as if it is a flat plate thermal boundary layer or a vertical plate boundary layer. So, that we use the correlation in terms of Rayleigh number. Rayleigh number is nothing but Grashof times Prandtl number, and you find the expressions for these in the textbook as it is a standard definition of Rayleigh number. And so, these two limits in the previous case, the D had a proportionality factor of Q is proportional to D square. In the isolated plate limit, the Q is proportional to 1 by D. So, with these two limits, now we combine them together and drew this, and if you equate the Q and you calculate a D for these expressions, you get an expression D optimum equal to 2.3 times height of the plate. This is the height, and the Rayleigh number based on the height is 0.25 minus 0.25. And the Q max is obtained after you take this Q D optimum and put it in any of the expressions for Q, and you will end up getting this expression. So, that is the method of matched asymptotes discussed by Bejan in his convection heat transfer textbook, and we use the same principle to derive a solution for a guiding principle for forced convection as well. And here we start with the assumption that there are two limits, again very similar to what we discussed, but what we are going to make, one is the D tending to 0 limit, the other one is D tending to infinite limit, and as is shown here, you are going to look at multiple parallel plates, and it is only a two-dimensional array is taken into account, not taking into account the bottom plane or the three-dimensional effects. And also we are going to ignore the thickness of the plate as we did in the previous case, and we are going to fix the pressure drop in this case as constant. We are going to develop the order magnitude analysis for a fixed pressure drop constraint, and with that we start with the same idea that D tending to 0 limit, very slender channel, that is essentially you have fully developed boundary layer growing all the way from the entrance to the exit. So, that is the common assumption for Poiseuille flow that one would have encountered. So, the Poiseuille flow velocity is d square u is d square by 12 mu, mu is the dynamic viscosity, and the pressure gradient delta p, the pressure drop across divided by the length is this. And then from the velocity one can estimate mass flow rate per unit depth, because we are considering only a two-dimensional array. So, we are going to treat the depth that is going into the page as unit, and so we write the mass flow rate as u into rho times h. H is the height of the channel, and that gives us this expression. Substituting for u for here, we get this expression for mass flow rate. Once we have mass flow rate, very similar to the natural convection case, we take m dot Cp into delta T, and if the plates are maintained at a certain wall temperature that is assumed to be constant, then the maximum temperature the outlet can reach is only the wall temperature. This is the Q for one channel, m dot into Cp into T wall minus T inlet or T infinity, which is the inlet temperature. And as you can see, if I plug this into the heat transfer rate per unit depth, I get an expression where Q prime is proportional to D square. So, what this says is that for the fully developed flow limit, as I increase the D, I get better heat transfer rate. So, this is the fully developed flow limit, and then we go to the D tending to infinite limit. Here one has to understand that now we are talking about internal flow, and for the sake of crude approximation we are ignoring the flow acceleration effects. We are thinking that the plates are so far apart there is no flow acceleration effect at the core, and just that we see only an isolated boundary layer developing and never merging before the exit of the heat sink. So with that, then one can treat this as using the Blassius solution, and with the Blassius solution one gets this expression for wall shear stress, and the wall shear stress 2n being the, because you develop boundary layer on both sides. So a single plate will have two boundary layers, that is acknowledged here in terms of factor of 2. N is the number of plates, and wall tau wall is the average shear stress over the wall, and that is given here. And from this we can estimate the velocity. This velocity, once we know, because pressure drop is given as constraint or constant, this is known, h is known, rho, all these are known, n is also can be calculated. With this we substitute in the Blassius solution to obtain the heat transfer rate as q prime, that is heat transfer rate per unit depth into k into delta T times this expression for Nusselt number. So with that expression we write it for the 2n, that is 2 is the number of boundary layers per plate, n is the number of plates, into per plate calculation. We get an expression for q prime as q prime is proportional to 1 divided by 2 by 3. As you can see, these two limits give us an opposing trend as we observed in the natural convection cooling, and if we go ahead and plot that, so this is our q proportional d square limit, that is as you increase the d, q increases. On the other extreme, which is the isolated plate, as you increase the d you get decrease in heat transfer. Where they meet is roughly where the optimum spacing is. And one of the beauty of this solution is that it gives us an intuitive solution, that what it says is that the boundary layers should grow in such a way that they merge right at the exit, very close to the exit of the heat sink is what is being discussed. So that is the solution essentially, that your boundary layer should merge right just before the exit of the heat sink. So that's when the optimum spacing is, this optimum d optimum is where the boundary layers merge just before the exit of the heat sink. So that's what we get, and we get as we did when once you know the two limits, essentially you equate the q prime where they cross over, then you get d optimum. Take the d optimum, plug it in any of these q equation, and you get q maximum. That's the maximum you can achieve. And these two limits, and you can do more rigorous analysis and do numerical and experiments, and you obtain the, so you get that roughly same order of magnitude solution for fin spacing. And that is, with that we conclude the part on heat sinks based on parallel plates. Now we move on to the next. This is the part 2 of the heat sinks lecture, is to focus now. We move from the parallel plate heat sink model and into more advanced modules. So what we focus on here is that moving away from the standard parallel plate, which is a workhorse or it is ubiquitous in throughout the electronics cooling industry or in heat exchanger industry, parallel plate or longitudinal fins are a very common occurrence in many of the applications over there. But here we will deviate a little bit from that, and because we discussed on one part 1 various aspects of the parallel plate heat sinks, now we will go into the aspects of some advanced heat sinks and how can we model those. If you look at the high performance heat sinks that are typically discussed, there is either a geometric modification or flow modulation, where convective boundary layers, the developing boundary layers are used, or one introduces either a swirl or vortices or some destabilization or turbulence intensification mechanism to enhance convective heat transfer. There are many ways one can actively do it by moving parts or passively in terms of making an array of ducts. Essentially an array of ducts consists of hexagonal array, triangular array, or square array, rectangles and so on, where you increase the surface area and somehow manage the increased surface area as a way to increase the overall heat transfer coefficient. But one has to understand that even though these complex geometries are discussed, the parallel plate heat sinks are still very robust in terms of performance, reliability and also in terms of mechanical strength. So, these are advanced structures tend to have certain advantages over parallel plate heat sinks, where the performance is more or less needed for in a guaranteed sense. Then we look into all these different aspects, where porous media these days, foams or stochastic foams or periodic foams can be used, where you introduce flow obstacles inducing mixing. Because one of the things that happens in a parallel plate heat sink is that the boundary layer, if I am looking at it, the boundary layers are growing, but these part of the flow is underutilized. That means it is still at the incoming temperature and there is no, the boundary layers merge, especially if they are merging right at the exit, as we discussed in the previous module or the previous lecture, is that now this area is underutilized. How can we utilize them? Because this is stratified and this is colder flow, colder temperature versus warmer temperature. So, if we can mix both of these streams, then we may end up getting more performance, heat transfer performance, and that is achieved through introduction of porous media or any flow obstacle in the flow stream. The last bit is the laminar flow instabilities. Instead of triggering turbulent flow, one may have a wish to introduce laminar flow instabilities and have closer to laminar unsteady flow effects. This we will discuss briefly also as part of the next part, that is as part of this advanced heat sink module. Let us first look at 2D array of flow ducts, and as we see here, these are the various embodiments or ideas that one can encounter. Is that you have a heat sink where there is a heater at the bottom and there is some heat sink, and it can have filled with hexagonal array of fins or square array of fins or triangular array or rectangular array, and some of these aspects is such that you need to know the local geometry. L sub w here is the spacing, local spacing between the walls, and the height of the rectangular section here is L sub h, and the thickness is half t by 2. So, you extract a unit cell and that is what you get, and the overall volume is fixed, which is width w, L being the length of the heat sink where the flow length, and h being the height of the heat sink. And we look into how do I model such a thing based on what we already know, instead of trying to do some numerical simulation or experiments. We will look at very simple models, and these are some nomenclatures we use, and this is for reference when you are looking through the slides. So, here is the example of how to model a honeycomb or a hexagonal based structure. So, we, as you may have encountered fin heat transfer, here we are going to look at a same fin heat transfer, except that now my fin is considered to be corrugated. In a minute we will understand why we need to do this, and instead of having a fin, the typical discussions in the textbooks would be a straight fin. Here we are considering a corrugated fin as a way to model this problem of flow through hexagonal or rectangular ducts. And we are going to assume that through the ducts, which are very small, that it encounters mostly fully developed flow type behavior thermally and hydrodynamically. So, but that assumption can be relaxed. For now, we are going to assume fully developed flow and derive this set of equations, and you will find that ultimately it leads to the same heat exchanger theory type solution, where M1 resistance of the heat sink is nothing but 1 divided by m dot mass flow rate times Cp specific heat times the effectiveness. So, here we write the fin equation in terms of d square, the partial derivative. square divided by the second order partial derivative in the local coordinate C. And otherwise, assuming a thin fin approximation assumption, this is very standard fin equation that you get when you consider where the bottom wall is given or T base is given, and which can be treated as T wall, and the top is considered to be adiabatic, that is adiabatic tip assumption. With these, now we use the standard relationship where the boundary is given T, the boundary condition is that T equal to T wall at psi equal to 0 and at psi equal to h, which is this height, we get adiabatic q dt by d psi equal to 0 at psi equal to h. So, from any textbook one can derive this solution that you, for the solution, the general solution is known, and applying the boundary conditions we get T equal to Tf. This is the fluid, local fluid temperature. We are not using, typically in a single fin solutions, we assume that the outside of the fin the ambient is at some heat transfer coefficient times T infinity. The T infinity is considered to be constant. Here we acknowledge that as there is going to be a flow, there is going to be a fluid flow, the fluid temperature varying as a function of depth or length into the heat sink, that is x, in the x direction the fluid temperature is going to increase and not remain constant. So, we make use of that and we write in terms of fluid temperature as a function of x. This is still unknown, we will find that in the later upcoming slides. T wall minus T fluid of x, and this is the hyperbolic cosine function, and just rewriting 2h to this in terms of BO number is nothing but heat transfer coefficient, local heat transfer coefficient times thickness by wall thermal conductivity, the solid thermal conductivity. So, substituting and non-dimensionalizing, we get an expression. We keep this Ch as a constant. We will understand what the Ch does is that Ch will carry a value of 1 if there is no corrugation. Essentially, Ch acknowledges that there is some kind of corrugated wall that exists. So, if I want to now, this is just a corrugated wall, but if I want to attach fins to it and make it into a duct, so now we add attachments. So, this lateral fins have to be now added to these solutions. So, for now, first what we did was that we took only the corrugated wall and we took the height as Ch times h. The Ch is a factor that will tell us how much corrugation length is, the increased length of it. If Ch is equal to 1, then it is a straight fin assumption. Like in a rectangular duct, if I had a rectangular array of ducts like this, then my Ch is going to be 1. So, we are going to use that and we rewrite in terms of y coordinate and this, and you get this expression. And then moving on, we attach, we calculate for a single fin, that is per unit length, this unit length is going into the page, and we calculate a heat transfer rate which is minus Ks into thickness of the fin dt by dy y equal to 0. And this expression, using the temperature solution that we obtain here, we plug it in and we derive from this dt by dy at y equal to 0 and substitute it over here, and that expression is given here. Then, as I discussed previously, we attach these lateral fins. These attaching lateral fins, one can do more analysis by thinking that now I know my temperature, I go to this point, I figure out what is my temperature, wall temperature at this point, let us call that T1, and let us call this T2, T3, T4. Now, you can treat this as additional fin heat transfer problem where T wall T1 has an added fin here. So, you write another fin heat equation for fin heat transfer, then you calculate T from knowing that T1, and we can calculate this. But instead there is an approximate method for which there is just adding a factor of n, and this factor is tabulated in the upcoming slides. With that, for different shapes with n equal to 1.5 and so on, we will look at the table. So, with that we can overcome this additional analysis and just use this factor, and it works very well as well. So, use this factor that a single fin, now this one single fin has these additional attachment 1, 2, 3, 4, and they are captured here in the form of a factor of 1.5. So, moving on, so we take that Q1 and having this, now we have the total heat transfer rate. That is heat dissipated by this array of ducts. And in the upcoming module, we'll discuss how we can calculate the fluid temperature variation in the duct as well. And for that, we need to perform fluid side energy balance, and that we will take up in the next module. So, what we have discussed in this module is that we discussed the forced convection cooling of parallel plate fins, and the aim of that exercise was to obtain the optimum spacing and the maximum heat transfer rate one could obtain from a parallel plate heat sink if the fin efficiency was 100%. Then we moved to the advanced heat sink module, where we started to look into an array of ducts, and that is where we will conclude here today, and we will go to the next module and we will take it further for discussion. Thank you.